This is a help video for the Laplace Mesh Solutions game in Circuit Tutor Level 1. So we'll go ahead and enter that game. So this presumes, of course, that you've already viewed the introductory tutorial, which is under the heading of Laplace Impedance Simplification, which provides a lot of essential information for doing these types of problems. Now, it's always a good idea to look at some examples. Generally, I'd recommend clicking on Show Example here to view some worked examples before you try to start working the problems yourself. So in this case, I'm going to go straight into the game at level 1. And we have a problem here with an inductor and a capacitor, a couple of resistors, and a current source and a voltage source. In this case, they're both step function sources. So our first task here is going to be convert this from the time domain, where we have the henries and the farads and the functions of time, into the Laplace domain, where we're going to have only ohms and the S variable. The time will not appear. So starting with the 2 Henry inductor, remember the impedance of inductor is SL, so that's just going to be 2S. So we'll enter that here. And then the resistors are unchanged, so the voltage source, the V1S of t, that becomes capital V1S bar, so that would be 5 over S, remembering the Laplace transform of the unit step function, which if you don't remember it for any reason, you can pull that up using the Laplace transform table that's always available up here. Then the I1S of t, again, that's also a unit step function, so that's going to be 4 over S, since the strength is 4U of t. And then the capacitor, the impedance will be 1 over SC, so that's going to be 1 over the quantity, 3S. And again, parentheses being essential here to make sure that we divide by both the 3 and the S, otherwise we'd be multiplying by S. Okay, so having entered those, we'll click on Converting to Laplace Domain, and those values are correct. So our next task then will be to select the reference mesh for mesh analysis. And if you're not familiar with that concept, it is discussed in the introductory tutorial on DC mesh analysis. So we need to select the appropriate reference mesh, and that can be either the outer mesh, as done in most textbooks, or it can be one of the interior meshes. In this case, we want to have something that is connected to a lot of current sources, so that would be probably either of these interior meshes would be good. And we also want one that's connected to a lot of other elements, so the left mesh here would be a little bit better than the right mesh. So we'll pick that one as our reference mesh and place the halt symbol, the circle with the X through it, in that mesh. And then we'll click OK here. And now it's going to redraw the circuit with that choice of reference mesh and automatically draw and number the mesh currents for us. And it'll give us the instructions here, which you can review. And also, if you need help on entering the rational function expressions and the syntax on that in Circuit Tutor, this help PDF is also available always from the help menu. So you can also get that by clicking on the help button there. Okay, so now we need to, first of all, because we have a current source, we're going to write the equations for this, and we're going to begin by writing a current constraint equation for the one current source that we have, which is always required. So in this case, the only current going through I1S is this mesh current I2. So notice the I1 has been chosen counterclockwise, as you always do if you're using the outer mesh current. Remember that the outside of the circuit is a mesh, just like the interior sort of window panes are. Okay, so here we therefore just have I2 going through that mesh, so we'll put one variable there, equals the value, and so this is going to be I2. And then here, because it's going opposite that direction, we'll need a minus sign here. And then for the value of I1S, that's going to be 4 over S, so I just type 4/S, using lowercase s to match the labeling here. And then we check that equation, and that is correct. So we've done our current constraint equation. So next we proceed to write the Kirchhoff's voltage law equations. Remember, mesh analysis is based on a systematic application of Kirchhoff's voltage law. So we'll select that. And now we're asked which mesh we want to write that for. If we look at it, mesh 2 does not, that current does not go through any voltage sources. So that one, I1 is okay to write for mesh 1. I2, on the other hand, goes through a current source whose voltage we do not know. That's whatever it needs to be, basically. And therefore, we cannot write a KVL equation for mesh 2. But we won't need to either, because we already have a constraint equation for that current. So we'll do this for mesh 1. Select that as the mesh to write the equation. And now I'm going to go in the counterclockwise direction to match the direction of that mesh current, just because I think that's a little bit easier. So let's start down here in the lower left, and we'll first have a fixed voltage. So that will be this symbol here for a voltage source. Then we're going to have an impedance with, actually a couple of impedances with two currents going through them. So I could combine those impedances, but it's probably easier here just to make separate terms. Otherwise, I'd have to do some algebra. So we have two currents rather. So we need this symbol and this one again, or that term, I mean. And then over here, we have two impedances with just a single mesh current, I1. So that would be this term. And then all of that has to add up to 0, since we're back to our starting point in the lower left. Okay, so now let's go in that counterclockwise direction and fill in the blanks here. So this is first of all going to be the value of V1s, which is just 5 over s with the plus sign, because we're encountering the positive sign first in that source. And then over here we're going to have I1 is the current we're solving for. I2 is in the opposite direction, so we subtract that. And we're going to add voltage drops going again in this counterclockwise direction. So the impedance there would be the 1 over 3s. So we put 1 slash parentheses 3s, again, parentheses always being essential there in the denominator. And then the next term would be 8 ohms. So it'll have the same two currents, I1 minus I2 times now 8. And I'm using the tab key here to go easily from one text box to another. And then for the 2s, we'll have just I1 going through that, nothing subtracted, because this is the reference mesh whose mesh current we're assuming is 0. So that will just be the 2s. And then the second one would be I1. And we could have combined these into a single term if we like, but I just did it separately. So that'll be times 8. Okay, so we'll check that equation, and that is correct for our KVL equation. That's the only one we can write here. So then the last thing would be the sought current equation for the sought branch current. So we'll select that type of equation here from the menu, and that'll give us the appropriate set of terms we can use. So we're writing an equation for I naught, and we see I naught basically goes this way, and so there's only one current going through that, which is I1, and it goes in the opposite direction. There's no current here because that's the reference mesh, so we're going to have that equal to the negative of I1, since it goes in the opposite direction to I1. So now we'll check that equation, and it was correct. So now we notice we have two unknowns here, I1 and I2. There's no dependent sources. And we have 2 equations in those variables. So that is sufficient to solve, not counting the sought variable as a separate thing. Okay, so now we can click No More Equations. And now it's instructing us that we need to combine the coefficients of each variable in simplified form and enter that into the next form, which will be, and we can also clear fractions if we wanted to, say by multiplying by s or something like that, but I'm just going to skip that for right now. Okay, so here's our form for the simplified form of the equation. So the I2 equation is very simple, the first one, so we just put a 1 times I2, coefficient of 1, and the default of 0 for I1, and then this value on the right hand side would be our negative 4 over s. That's our constant. I mean, it contains s, but it's a constant as far as our variables I1 and I2 is concerned. Okay, and then the second one, that's going to take a little bit of work. So I've prepared that on paper here. So we need to find the the constant term, first of all, is going to be this 5 over s. So we'll put that on the right-hand side by subtracting it. So the right-hand side becomes negative 5 over s. Then collecting the coefficients of I1, we say here we have 1 over 3s, so that's the first term. Then we have an 8 here, so we have an 8. And then here we have a 2s, so that's the next term. And then finally we have another 8 for the other 8 ohm resistor, so that's over here. And then I've actually just crossed that out and made this into a 16 to simplify that a little bit. And then for the I2, we have a minus 1 over 3s coefficient here because of the minus sign. So that would, and I've just factored the minus out since it's going to be there for both terms. And that's the 1 over 3s. And then here we have minus 8, and that's it for the I2. So we have, again, factoring out the minus sign, we just have plus 8 inside the parentheses. So that's our basic equation, but we do need to simplify that into standard form where each of these coefficients is a rational function. So here our common denominator, since we're adding fractions, is going to be just the 3s. So that's pretty simple. So we multiply, well, here we just have 1 over 3s, and then here we have to multiply by 3s, so that becomes 16 times 3s is 48s, and then the 2s times 3s just gives us the 6x squared in the numerator. And then of course we can always check that by just dividing back and saying that yes, that's 1 over 3s, yes, this is 16, and yes, this will give us the 2s. Then over here we do the same thing, putting it over the same common denominator of 3s, which is convenient. And so that will just give us the 1 here, plus multiplying this by 3s over 3s gives us 24s, divided by the same common denominator is equal to negative 5 over s. So now we put that in simplified form. And I did rewrite it here, just putting it in standard order for the polynomials, so decreasing orders of s. And I've also noticed that we have an s in the denominator of every term. So it's always best to cancel out things that can be canceled at the earliest possible time, because that just avoids making things more complex later on. So it's always a good idea to be watching out for things that can be canceled. Then our other equation, of course, is just that I2 is negative 4 over s. We've already entered that one. So let's go ahead and put these this into the equation here. So for the second equation, the coefficient of I1 is going to be 6s squared, using the caret to square it, plus the 48s plus 1. And of course, that all has to be in parentheses, otherwise we wouldn't be dividing by the entire thing, and that's just dividing 3, so we don't need parentheses there. And then the I2 coefficient is going to be a negative, and then we'll have parentheses 24s plus 1. And then that, again, is divided by 3. And then the right-hand side is just going to be our negative 5 over s. Or, I'm sorry, we canceled the s, so it's just going to be negative 5. Right, so we've already canceled the s. So that should be fine, and now we'll check that. And that is correct. And it's printed on the screen now. So now we need to enter the matrix equation, but that really we can just do trivially by pressing this copy button here, since it'll have the same coefficients. It'll save us a little typing here. So we'll copy that in the same format, and then we'll just check that, which of course will be correct. And now it gives us instructions to go ahead and solve and to keep records of what we're doing. So this is the hard part probably. We have to solve for I1 and I2. Now let's look at our SOT variable first of all to see what we really need. We really just need I1 because that's our SOT variable. Now, however, I2 was the one that we already basically have. That's the trivial one here. So we really need both variables. So we won't bother skipping to just enter the final value because there'd be no point here. Okay, so we'll just go ahead and enter the easy one, which is negative 4 over s. And then for the I1, we're going to have to do a little bit of work here to solve the simplified equations, which are the ones right here on paper. And so in order to solve for I1, that's pretty simple. I can just plug in this simple value for I2 here. And then we're going to put all the constants on the right-hand side. So I factored out a minus sign here since everything's going to be negative on the right. So we just have, and we've already canceled that s, so we just have 5 here. And then we have to, basically, this is now a constant term since we got rid of the I2 by substituting, so we're going to bring that over to the right-hand side. And because of this minus sign, it's going to be positive, so it's going to be negative when it gets over here, and we've already factored out the minus sign. So that's going to be basically the 4 here times the 24s plus 1. And then we're now dividing by s again because of this s. And so we have that. And then having put all the constants on the right-hand side, then we just cross-multiply by the coefficient of the I1 to solve for I1. So that means we multiply by the 3 divided by this quadratic denominator here. So now we have this expression. And now, of course, we need to put this into a proper rational function, which means we have to, once again, add these fractions. And the common denominator, of course, will be 3s here. So basically, I have to multiply this by 3s over 3s, so that becomes 15s. And then here, just multiplying this out so I can combine it with the first term. The 4 times 24s will give us 96s, and then the constant will be 4. And then the common denominator is 3s. Now right away I'll notice I've got a common factor of 3 here, so I'll cancel that out. Again, trying to keep things as simple as possible to avoid extra work. And then just adding this up now, combining it, the 15 plus 96 times s, that's going to be the 111s. We still have our minus sign. And then the constant, just 4. And then we do have an s now in the denominator, and then we have this quadratic term. So that is the form of I1. And we can basically enter that now. And so I'm going to put a minus sign times 111s plus 4. And we don't have to do any factoring at this point. I mean, you could, but it's not required. And here I'm going to put a square bracket because we're going to have multiple terms inside that bracket. So we have s times the 6s squared plus 48s plus 1, close parentheses, and then we have to close the square bracket. Remember, we're not allowed to put parentheses inside of parentheses except for simple fractions, which we don't have here. Okay, so that's the correct format. So now we'll go ahead and check that. And that is correct. And then it's going to tell us that we need to use the SOT variable equation, which is just I naught equals minus I1 to find I naught. And also it's going to tell us that at this stage, because we're going to have to do an inverse Laplace transform on I naught, that we want to prepare it for doing partial fractions, which means we're going to have to factor any quadratic terms that appear in the expression. In this case, there's one in the denominator. And so it'll have to be in factored form when we put it in here. Just so that can be checked before we start the before we start the partial fractions. So in order to factor the denominator here, we can just use the standard quadratic formula. So if we have ax squared plus bx plus c equals 0, then the roots will be x equals negative b over 2a plus or minus the square root of that same thing squared minus c over a. Again, that's the sort of improved form of the quadratic formula. And and also, I just say I naught of s is minus I1 here. And also, to prepare it for that, I did pull out a factor of 6 here. That makes it easier to apply this formula. So pulling out the 6, that makes this just s squared, and the 48 over 6 is 8s, and then the 1 becomes 1/6 or 0.1667. Okay, so just normalizing that makes things a little easier when we're doing the quadratic formula, and we won't have to remember to put in the extra constant. It's not essential, but I like to do it. And so now we apply the formula. So we have negative b over 2a. That's going to be negative 8 over 2 is negative 4, of course, plus or minus the square root of that same thing squared, which would be 16, minus the c over a, which is just this constant. And then putting that in a calculator, that gives us two roots, a small one and a big one, so minus 0.02089 and minus 7.979. Those are both going to be in inverse seconds, because remember, that's the units of the complex frequency always. And it is important to make sure that you carry through significant digits. So don't, for example, round this to 0.02. That would be giving you only one digit of accuracy, and that might not meet the accuracy criteria of the answer checker. And you sure wouldn't want to lose credit for a problem just because you didn't type enough digits. So make sure that you always put in at least 4 significant digits. That's not 4 digits beyond the decimal point, that's 4 significant digits, right? So the 2 is the first significant digit. You don't count the zeros, okay? So now we'll use that to factor the denominator here. So we have the 11s plus 4 in the numerator, the 6s still, and then basically factoring this. Remember that because this is negative, we have to take s plus that value, and then also s plus this value, because otherwise these wouldn't be the roots here. If we put a minus here, that would be incorrect as far as the roots is concerned. So we have to make sure we do that properly, following standard rules of algebra. Okay, so that's our formula for I naught. And now I'm just going to enter that into Circuit Tutor to check it. So I have 111s plus 4 divided by, and then I'll again need a square bracket in the denominator to enclose the other terms. So then we'll have 6s times, and I don't really need to put that in parentheses because it doesn't need it. So I have s plus 0.089, close parentheses, and then the next term would be s plus 7.979, close parentheses, and then close the square bracket. Okay, and I'll just proofread that quickly. Looks correct, so we'll check the answers there. And it is correct. So the next step is going to be to do a partial fraction expansion. So we'll just click OK there. And for some reason, it's going back through and asking us to repeat these things. And I'm trying to track down that bug, but whenever I try to track it down, I can't repeat it. So only when I'm recording videos, of course. So anyway, we'll repeat that entry. I'll try to reproduce that error so I can fix it. And we have to do that again. So okay. So hopefully this time it'll really take us into the partial fractions. So select partial fraction expansion, and now we'll need to work that out on paper. So we have I naught of s equals, and then we know that we're going to have basically, since we have 3 poles, one at the origin, one at the minus 0.02089, and one at minus 7.979 are the poles. Here are these values. So we're going to need 3 of these terms. And those are all going to be in units of amps because it's a current. So we'll just select that right away. And then let's work out the actual values. And in fact, we already know the denominator here is going to be s. And the denominator here is going to be s plus the 0.02089. And then this one is going to be s plus 7.979. And by the way, we already know, because these roots are negative real numbers, that this system is going to be overdamped. So its natural response here is going to be decaying exponentials. We can anticipate that already just from these values. Okay, then we need the coefficients. And so to compute those, I've done that here. So I've written out the expansion, a over s plus b over s plus 0.02089 plus c over s plus that value. And then to find, for example, a, I'm going to use the heaviside or cover-up method, or method of residues it's also called. So we'll multiply by s here. That cancels out the s here and puts an s in the numerator here and here. So then we set s equal to 0. That gets rid of these terms entirely. And then we just evaluate this by setting s equal to 0 in all the remaining terms. So we just have, this term goes away, we just have 4. Then we have the 6, this term is gone because it canceled. Here we just have what's left, the value there, and here just the value carries down, and then doing the arithmetic there, that works out to be almost exactly 4. Then to find b, we multiply through this by this denominator all the way through, and then set s equal to minus 0.02089, that is the value of the pole, and that will wipe out this term, and it'll wipe out this term by virtue of that factor. And then here, of course, it cancels. So in this case, when we set 111 times that value, that minus 0.02089, and then the plus 4, of course, and then we have the 6, and now the s didn't cancel, so we have to put the value s there, And then this is the term now that canceled, so that's gone. So we just have this term, and we put in the s there, same value of s, plus the 7.979. And then we just do that math on the calculator, and that works out to be negative 1.686. And finally, to find c, by a similar process, we multiply through by s plus 7.979, and set s equal to, you guessed it, minus 7.979. And that will wipe out these two terms, and also we're going to cancel out this term here. And so then we just substitute that value of s into here. So 111 times that value plus 4, and then the 6 times that value. And then this term is the one remaining now, so it's that value plus the constant. And then once again, do the arithmetic, and that works out to negative 2.314. So those are the three coefficients that we need. So we'll go ahead and enter those here. So that's going to be a 4. And here it's going to be, well, it's a negative, so I think I'll just put the negative sign out front. Doesn't really matter. 1.686. And this coefficient is also negative, so I'll put a minus sign there, 2.14. You can also put it in the numerator here if you want, but it doesn't matter. Okay, so that should be correct. So we'll check that. And that's now been printed on the screen for us. You have to scroll down to see it. See a lot printed on the screen. So that means we've done all the partial fraction expansion. So we just click no more equations. And then it tells us we're going to have to do the inverse transform. So wait for it to bring that up, and then we have to select that equation type, the only choice. And it'll also point out that we do have radio buttons here, because there are some terms that we might occasionally need that are on a second set there. Which you can see if I click over, there's some additional terms which we won't need for this problem, but you do need them sometimes. So now we'll think about what terms we need. So basically we have, based on the partial fraction expansion, and I'll scroll back down to that again. First of all, we want everything multiplying u of t and the units. So I'm going to put everything basically inside a set of brackets. So I can put a left bracket here, and then I am going to have a constant term times the u of t, because the inverse transform of 1 over s is just a constant times u of t. So I'll put a constant term there. And then here we recognize that hopefully as the Laplace transform of an exponential, a decaying exponential. So we're going to put that type of term there. And again, if you didn't remember that, you could bring up the Laplace transform table at any time here to see what that would be. And then another of those for the second, or the third term rather. And then finally we have a closed bracket, and then we need the u of t always, and then we'll have the amps, or the units, to make sure we have units on our answer. Okay, then we just need to fill in our numbers here. So that's going to be the 4. That's the coefficient here. And then this is going to have a minus sign. And that will be the coefficient 1.686. And the exponential should always be a decaying exponential, unless it's an unstable system, which this certainly cannot be. And then here we need our time constant, which is the reciprocal of the a value. Remember that this is the a value, or the rate constant in units of inverse seconds, like s. Since it's added to s, it has to be. And so I've just done the math over here. 1 over that rate constant of 0.02089 inverse seconds is 47.87 seconds. So that'll be the time constant. And then this coefficient would be the minus 2.314. And once again, that has to be a decaying exponential, very important. Then that rate constant here for the 7.979, that's inverse seconds, so we take its reciprocal to get the seconds, is 0.1253. Oops. And looks like that should be correct, so we'll go ahead and check that. And it is correct. And now we just say no more equations since we're done entering the equations. It has been printed on the screen. Again, it's kind of down low, down here. So we'll say no more equations. And it is going to give us the usual PDF transcript, which is shown here, which shows all the steps that we took. And if you made mistakes, then it would show those mistakes as well in red, just so you can learn, of course, not to repeat them. And we can access those from the review work menu. And if you had any questions about how to work this, of course, you can go back and see a detailed explanation if you wish. And that'll just show basically the computer's version of how to solve it, which should be very similar to what we did. But it shows the conversion from the time domain to the Laplace domain, and then illustrates the formation of that equation, color coding the different terms. Just like in an example when it shows examples, basically. And then it shows all the steps here. Let's expand that out. It shows all the steps there. And we could even, if we wanted to see how it does Gaussian elimination, you could show that here. Although, again, I don't really recommend that as a method to solve because it's usually more complicated. Okay, so I'm just going to close that up now and remind you that you can review work here. And that's basically it. So that concludes this example.